All right, so we only have two things left to do. Now, of course, remember the exam is next week, which is May the 11th at our normal time in our normal classroom setting. And so all the reviewing is done except for the last two parts, Chapter 12's problem set and the actual sample finals. So that's what we're going to do right now. And then we'll be done. Okay, so now that doesn't mean you can't still ask questions. You can certainly send me emails, but this will be the end of the reviewing. Okay, so let me just get this one open and we'll get started. So with Chapter 12, this is where we introduce limits and derivatives. So we're going to have several questions about both of those. Now, the limits are pretty straightforward, at least the ones we're doing. Limits can be obviously a lot more complicated than what we're seeing here, but the basic cases are not very difficult because for the most part, you're really just substituting a value into wherever you find X. And so, for example, this first one is even easier because you don't have anything to substitute into. There are no variables. So the limit of 3 is just 3. Okay. The limit of any constant is just equal to that constant. Now, for the next one, though, it's the limit as x approaches 4. And so what we'll end up with is just simply putting 4 in here for x. We have 16 plus 7 equals 23. Okay, so you can see it's really not that difficult, but you won't see the more complicated ones until you get to Calc 1. Okay, then it can get a little messy. Sometimes, for example, you might have cases where you wind up with division by 0, and then it turns out that you can actually sometimes take steps to avoid that. And in other cases, the limit may simply be undefined. But here we're sticking with the cases where there is a limit, and it can be obtained simply by plugging in the correct numbers. So here, for example, we have the limit as x approaches -2. We're going to plug in -2 for x. So 2 to the -2 to the 4th power is positive 16. And so this one is simply 48. Okay. Now here, we're replacing all the x's with 1. So we simply have 2 times 1 squared plus 5 divided by 1 minus 3. So we have 2 plus 5 over -2. Wait a minute, what did I do here? I'm sorry, yeah, 7. No, I just wrote the wrong thing. What did I do here? Hold on, 2 plus 5. Okay, but it will end up being 7 over -2. Or often what you'll see this done, written as is just simply -7/2. And instead of doing that, you can write it, if you want, as -3/5. It doesn't really matter. All of these are fine. Well, all right then. Let me just check one thing. All right, looks like everyone's muted. All right, good. All right, now what about this one? X equals 0. This will be particularly simple because all the x's become zeros. And so that you can see that basically just leaves the -1 cubed, which is -1. Now, this next one is a little bit challenging. It's a little bit complicated, but once you get the hang of it, it's really not that difficult. What you're really doing is saying, all right, we're taking this limit. And when we're done, by the way, this will give us the derivative of this function. And which we know how to do algebraically, but this is the formal definition of what a derivative actually is. It's a limit. That's all it is. It represents a rate of change, but it is formally defined as a limit, or at least the limit of a difference, which gets smaller as x approaches 0. So the tricky part here is f of x plus delta x. What exactly is that? Well, what we're really doing here is just replacing all the x's with x plus delta x. So I picked a fairly straightforward case, and if this shows up in the test, I'll do the same thing because, there's no point in making it too messy. We're trying to learn the principles behind this. So what exactly is x plus delta x squared? So a couple of ways you can go about this. You could use FOIL in this case. In fact, maybe we'll do that. All right, instead of what I was about to do, let's try FOIL. But before we do that, let's remind ourselves that this is equal to x plus delta x times x plus delta x. So that'll work better with the FOIL definition. So if you remember how that works, you've got FOIL. F means the first terms in each set of parentheses. O is the outer terms, x delta x. I is the inner terms, again, x delta x. And then last would be these two terms, delta x squared. So when you combine these, you'll have x squared plus 2x delta x plus delta x squared. All of this is what we mean by f of x plus delta x. But we're not done because the definition tells us, let me just copy this down here, that we need to write out this following expression. So what I'll have, now we already know what f of x is. This is our f of delta x plus delta x. The original function up here you can see is x squared plus 4. Okay, so actually let me repeat these down here. F of x is equal to, oh, you know what I just realized? I forgot about the 4. Yes, this p squared gives us this result, but we don't want to forget about the 4. That's an important part of it. So f of x plus delta x is actually what you're seeing here. So let me copy that down here somewhere. And then that way we can see what this formula is asking us to do. Oops, actually, let me clean it up a little. All right, so once again, f of x was originally x squared plus 4, f of x plus delta x is x squared plus 2x delta x plus delta x squared plus 4. So in this limit formula, we're basically just taking the difference of those two. All right, so the numerator will look like this. So we have x squared plus 2x delta x plus delta x squared. Whoops, almost got it, almost did it again, plus 4. And then we're subtracting the original function. And then in the denominator, we just have delta x. Now, often the delta x will cancel out with some of these terms, which will make things a lot simpler. So let's see if that happens here. So I'll just drop the parentheses. It means I'll have minus x squared minus 4. Remember to apply the negative to both of these terms. Divided by delta x. And now there should be some opportunities to cancel here. So in other words, these two cancel each other, as do these. And so we're just left with 2x delta x plus delta x squared all over delta x. Now, if you notice, both terms in the numerator have a delta x in them. So
got a little something to smoke.
We'll cancel with both of them. Okay. All right, just making sure everyone's muted. So then you'll end up with the limit is delta x goes to 0 of 2x plus delta x. Now, with all that being done, now you can actually apply the limit itself. So remember, all you're doing is replacing delta x now with a 0. So you end up very simply with just 2x. And now we've already seen the rules that will enable us to calculate this directly. And so the original function was x squared plus 4. So why don't we confirm this with our rules? F prime of x equals. Now, when we have an expression like this, we're going to have, let's remind ourselves, this is the power rule, nx to the n minus 1. Okay, so here, that's going to be 2x to the 2 minus 1. The derivative of a constant is just 0. So we actually end up here with 2 times x, and we're done. So either way, you have the same result. It's just that the first way, this way, is done with the formal definition of the derivative, and the second approach uses the rules that we developed. Now, most of the time, you'll want to use the rules. This formal definition is very time-consuming, but it's important to understand what exactly a derivative means. You can think of it as simply the rate of change of the function at a given point, or the slope of a tangent line. So let's see, x squared plus 4 looks something like this. So let's just say I randomly pick the point x equals 3. The slope at that point is the slope of that tangent line, and that's equal to f prime of 3, which means 2 times 3, which means at exactly that point, the slope is 6. The derivative of this is therefore 6 at that point. At every other point, you'll see the slope can be different. Okay, because this is not a straight line, the slope will be different at different points on the function. So if we're interested only in a particular point, we can find out what the tangent line looks like by plugging in x into the first derivative. All right, now, why would you need to do this? Well, this is very useful for optimization problems where we might want to know, for example, what would be the optimum amount of units for a company to produce in order to maximize their profits, or what would be the optimum number of units to produce to minimize their costs, that type of thing. Those are called optimization problems because we're trying to figure out the best choice. We're trying to optimize our profits, basically. So yeah, and we'll see, if you've ever been in an economics class, you see this all the time. We use concepts like marginal cost, marginal revenue to help us identify the best points of reduction for a firm. And those marginal concepts are all just derivatives themselves. All right, now here we can use the rules, all right, that we define. There's quite a few of them, as a matter of fact. So we'll start with a simple one. In this first case, we called this the constant function rule. And this is as easy as it gets. The fact that 3 is a constant means that its derivative is just 0. Now, the reason for that is because the derivative is a rate of change. And a constant doesn't change. So therefore, it makes sense that the derivative of a constant would just be 0. Okay. Now, for this next one, we're using the so-called power function rule, which we just used a minute ago up here. This one, this is a simpler version of the power function rule. And so the way it works, let's just review that one more time. In the most general possible terms, if f of x equals kx to the n power, then f prime of x is n times k times x to the n minus 1 power. So for here, we have two terms. The first term, the 2x squared, we can apply this rule and we get 2 times 2 times x to the 2 minus 1. Then we don't have to worry about that 7. It's just a 0. The derivative of -7 is 0. So when we're done, the derivative is 4x. That's it. We don't have to worry about the -7 because it's a constant. most of the time with polynomials, you're going to wind up with something just like this. Some of them are a little bit more involved, but many of them are based on this power function rule, as it's called. And then here's another example of this. We're going to apply the same thing, use the power function rule. So we're going to have, I remember the pattern, if f of x is kx to the n, and remember k and n are just constants. X is the only variable in this equation. So for the first one, you'll have 3 times 4 times x to the 3 minus 1. And then now here you'll have minus 2 times 2, x to the 2 minus 1. And then for the third term, keep in mind that there's an implied 1 here. So 1, 5, x to the 1 minus 1. And so you end up with 12x squared minus 4x to the first, which is just x, plus 5. Now, x to the 0 is 1. So when you simplify this, what you end up with is f prime of x, the first derivative, is 12x squared minus 4x plus 5. Okay, so x to the 0 is just 1. So this is our final result. And you can't actually simplify it any further, so you can just leave it like that. Now, we're ready for the complicated ones. We've got rules that help us with cases like this, where we've multiplied two expressions together. Now, here you've got a couple of options. You could actually apply FOIL to that and just come up with a string of variables and then apply the general, the function rule, power rule rather. But here we'd like to use the product rule. And let me just remind you what that's all about. And this, by the way, this is probably going to wind up being simpler anyway. If f of x equals a product of two other functions of x, which we'll just call g of x and h of x, the product rule basically says that when you differentiate this or take the derivative, you'll end up with g of x times h prime of x plus h of x g prime of x. So it's a bit messier than you might have thought. It's not just the product of the two derivatives. So what we should probably do, just to keep it simple, is first make sure we know what's what. So g of x could be this 2 plus x. H of x is the second term, 7 minus 2x cubed. And then while we're at it, let's calculate these derivatives. Now, here we're just going to wind up with 1. The derivative of x by itself is just 1, based on the power function rule. Okay, just remember that. When you see the derivative, these are the two simplest cases. A constant has a derivative of 0, and just plain old x by itself has a derivative of 1. And that's because with x, it's actually 1 times x to the 1 power. And so if this is your g of x, then g prime of x would be 1 times x to the 1 minus 1, or x to the 0, or 1. So that's why that's happening. Now, over here on this side, h prime of x, the 7 just drops out. So we end up with minus 3 times 2 times x to the 3 minus 1, minus 6x squared. Well, now it's just a question of substituting into the this definition. And so we'll just plug away. Now, you don't have to bother simplifying it too much, unless it's really straightforward. You can just leave it the way it is. You'll see what I mean in a second. So 2 plus x for g of x. H prime of x, as you can see, is minus 6x squared. H of x, remember, is 7 minus 2x cubed. And G prime of x is just 1. So that, you don't really need that. So you can simplify it a little.
I have a question.
Yes, go ahead.
So what happens to like when you do like the derivative part of like the G and H, the numbers outside of the X, you just leave as it is, like there's no including it?
Like which part?
Like 2 plus X, right? Like you said X just
Oh,
equals
yes,
to
yes,
1.
yes. So this is just 0. And
Okay.
then, yeah, this is just 1. So in other words, this really, I guess what I should have done is written it as 0 plus 1. And then that just left me with 1. But this is the explanation for why x has a derivative of 1.
So the numbers outside of the X's don't count. Exactly what you're saying.
They do. I'll tell you why. Let me show you another example, just so to get this clear. Suppose that instead I had this example. F of x is 3x. And keep in mind, there's implicitly a 1 here. Okay. So f prime of x would be 1 times 3 times x to the 1 minus 1. 3x to the 0 is just 3. So it'll be the coefficient of x. That's our derivative. Now up here, there's an implied coefficient of 1, which is why this ends up being 1. So that's why it worked out that way. So you're using the general power rule. And then the rest, like I said, we're just substituting. Now, this next one is the quotient rule. Okay. So with the quotient rule, it's a little bit messier. In fact, it's quite a bit messier. So this is what it looks like. Wow, what a mess, huh? So that's our quotient rule. Now, in this particular case, so what we should do is identify which is g of x, which is h of x, and then we can make our substitutions. So g of x is the numerator. H of x is the denominator. 8x squared minus x plus 1. So g prime of x. Now remember, that 9 is a constant, and here we have just 4x. So based on the reasoning we had before, this is just 4. Okay, it's actually 4 plus 0, which is 4. So whenever you have just x by itself with some coefficient or other, the derivative is equal to that coefficient. Okay, now over here though, well, actually the same thing is going to happen. We're going to have 2 times 8, x to the 2 minus 1. Here the coefficient of x is -1. Okay, so we end up here with 16x minus 1. Okay. Always remember, f of x is kx to the n, f prime of x is nkx to the n minus 1. We're going to get more use out of that rule probably than any of the others. And so that's why this one reduces to -1 right here. So it's whatever is the coefficient of x, that becomes your derivative. With the constant 1, it's your derivative is just 0. But now we just have to do some substitutions. So the derivative of this function is 8x squared minus x plus 1, that's h. G prime is 4. G is 4x plus 9. H prime of x is 16x minus 1. And then in the denominator, we simply square the h. And that's it. You don't need to go nuts trying to simplify that because it's going to take forever and it doesn't really help. I mean, unless you need a specific result, but that's fine. And then there's one more. Now, this is that case. It's a little different because you're raising a polynomial to an exponent. So this is sometimes called generalized power function rule. And the way that works is that if you have f of x equals g of x raised to the nth power, which we have here, the derivative is n g of x n minus 1 g prime of x. So in our example, g of x is 6x cubed plus 9x. G prime of x is 18x squared plus 9. Okay, and again, we're using this rule for each case over here. And then n, of course, is 2. So our final result, f prime of x is,
Wait, sorry, how do you know n is 2?
oh, because up here it's this is the 2 right here.
Oh, okay, thank you.
Okay, so I have 2, original g of x, and the exponent is n minus 1, which in this case would be 1. And then you'll have g prime of x, which is 18, x squared plus 9. Now, of course, we don't really need that. I mean, if you want to simplify it a little, you don't really need that 1 there. And that's it, you're done. Wow, all right, now in this next group, we're looking for this second derivative, which just means you're applying the derivative twice. Okay, it's no different, it's just that you have to go through the steps a second time. So, and again, we're going to see this generalized, the power function rule rather, used many, many times. But remember, this is just a constant. So you're going to wind up with 7 times 8 times x to the 7 minus 1 plus 0, because that's the constant. Okay, now normally we'd be done, but now we need to do this again. Okay, the second derivative, which we write as f double prime of x, we're reapplying the rule. So we'll have 6 times 56, x to the 6 minus 1, 336 x to the 5th, and that's it, you're done. All right, now let's try B. So again, just remember the second derivative is just you apply the rules twice. That's really all there is to it. And of course, we could do the same thing if we wanted to. We could have a third derivative, a fourth, a fifth. You can have as many as you want, but eventually all of them become 0. All right, let's try this one. All right, so f prime of x. Now, if there's first one, it'll be 5 times 2x to the 5 minus 1 minus 4, 3, x to the 4 minus 1 plus 2x to the 2 minus 1. And this last one is just 0. It's a constant. 10x to the 4th minus 12x third plus 2x to the 1st, which means just 2x. And now we can apply the second derivative by applying the exact same rules. 4, 10, x to the 4 minus 1, minus 3, 12, x to the 3 minus 1. And now here, remember, we saw that earlier, it's just 2. When you have just x by itself with some coefficient, the derivative is just 2, or that coefficient. So we end up finally with 40x cubed minus 36x squared plus 2. All right, and then there's just one more. Same thing, we're applying our old friend, the power of function rule. 8x to the 8 minus 1 minus 7, 5. Oh, by the way, I guess I should be consistent here. This is actually 8 times 1, because just x by itself, or x raised to the 8, there's implicitly a 1 in front of that x. Okay, not that it affects the results. So we end up with 8x to the 7th minus 35x to the 6th. For our first derivative, and then for our second derivative, 7 times 8 times x to the 7 minus 1 minus 6, 35 x to the 6 minus 1. 56x to the 6 minus 210x to the 5th. Beautiful. All right, now this last part, it says the words relative extrema. Let me show you what that means. Extrema, it's a Latin word. It means the extreme points. These are the minimum points or maximum points, or there could be some of both. So write it like this: minimum and or maximum points. Now, how do you find them? Well, for this first one, this is a parabola. It faces up because the coefficient of x squared is positive. So what we're looking for is the point where the parabola reaches its minimum value, right about here. There's going to come a point on this curve where the slope is 0. It's flat at that point, and that's what we're aiming for. And because of the way this function is shown, you can see that this will be the minimum value that this function can achieve. Now, how do we find it, though? Well, it's a two-step process. First, calculate the derivative f prime of x, and then number 2, set f prime of x equal to 0 and solve for x. All right, now in these cases, it'll be very straightforward. You can see there's exactly one extreme point, the minimum, so it won't be hard. If we had more complicated functions, it could get very messy, and there could be more than one extrema, as they're called. But here, they'll just be the one. If it was a cubic function, for example, there could be 2 extrema. There could be, for example, 1 minimum and 1 maximum. But here we're keeping it simple. So the first derivative, based on the rules we've been developing, 2, 4x to the 2 minus 1. Now, here, remember, this is just some constant multiplied by x. That's going to be just 8, because that's the coefficient of x. So this one ends up being 8x minus 8. Now, if we set this equal to 0, 8x minus 8 equals 0. 8x equals 8. and x equals 8/8, which is just 1. So what that means then is the point here, although this isn't drawn exactly right, let me try that again. X is 1. Now, if you want to know what y is, or f of x, plug that number back into the original function. You'll have 4 times 1 squared minus 8 times 1 plus 10 equals 4 minus 8 plus 10 is 6. So that means x is 1 and y is 6. Try this one more time. So that point is the minimum because the function can't go any lower than that. In other words, f of x cannot fall below 6. That's the minimum point. When x equals 1, the function is equal to 6, and that is the minimum point. After that, the f of x is always higher than 6. So it could actually be known, you could actually call this the relative minimum. The opposite of that would be the relative maximum, but they're both examples of what we call extrema. Okay, now for this one, we'll have the opposite. This is a parabola that faces down. You can tell because the coefficient of x squared is negative. So whatever point we find here is going to be the function's maximum. Something like this. So we'll do the same thing. We'll take the first derivative. 2 minus 3, x to the 2 minus 1, minus, again, we have 6x, negative 6x. The derivative is just negative 6. The constant is just 0. So the derivative ultimately ends up being minus 6x minus 6. So we're going to set that equal to 0. And it looks like just by, oh, no, actually, it's not the same. All right, let's find out. This tells me that negative 6x minus 6 equals 0. Minus 6x equals 6. X is 6 over minus 6. X is negative 1. All right, so the graph is a little bit off. It should have been on this side. Let's see if I can do that. Sometimes I can with this tablet, but sometimes I can't. Just fix individual elements. So let's try that again. It's going to be over here somewhere. X is negative 1. So if we need to know what y is at that point, just plug that into the original function. So we have f of negative 1 is minus 3 times minus 1 squared, minus 6 times minus 1, plus 2, and that leaves us with, now minus 1 squared, of course, is just 1, minus 3 plus 6 plus 2, and that gives me 5. So the point here is negative 1, comma 5. That's my maximum point. Okay, and there's only one maximum. There's not going to be more than one. There's no minimum. So we're completely finished with that one. All right, so that was our chapter 12 problem set. Now we're ready for the sample final. Now, of course, as usual, I'll post these on Blackboard, Moodle rather, when we're done. So here we've got some fill-ins, of course, and then we have quite a few questions from chapter 11. And then, of course, we still have some more calculus here. So let's see what's going on here. First of all, what is a permutation? Well, A permutation, you recall from chapter 11, is a case where we're selecting objects from a larger collection where the order of selection matters. That's the key to the whole thing. The order of selection matters. So like license plates would be a good example of that, because the order of the letters does matter. It really does make a big difference. So, but with other areas, like if you're trying to choose toppings for an ice cream or something, the order of selection does not matter. And so what we have instead is a combination, because here a selection of objects from a larger collection where the order of selection does not matter. That's the difference between the two. Does the order of selection matter or not? Now, arrangements just means you're taking the same objects and changing their sequence. So when we have 6 objects, we can create 6 factorial, or 6 times 5 times 4 times 3 times 2 times 1, or 720 arrangements from 6 objects. Okay, so it's always n factorial. All right, a sample space. Now this is, again, probability theory. This is a set of all the possible outcomes of a random experiment. So like if I flip the coin twice, you saw already, you can have 4 possible outcomes, and they all are put into this sample space. An event then, which is what we normally end up calculating probabilities for, an event is simply a subset of the sample space. Okay. In other words, it's a set of things that can happen, but it doesn't necessarily represent everything that can happen. Okay, now, let me just throw a quick example here. Suppose that you had flipped a coin twice. Your sample space would consist of all the possible outcomes: 2 heads, heads followed by tails, tails followed by heads, tails followed by tails. The event could be something like this: at least 1 head. And that would be a set that contains HH, HT, and TH. And you can see that A is a subset of S because all the elements in A belong to S. And that's all there is to it.
I have
Now,
a question.
yeah, go ahead.
So it says a random, like it says like at least 1 head. Doesn't that mean there's like 1 head and no tails? I mean 2 tails, something like that?
At least 1 head means either 1 or 2. The only thing it rules out is two tails, because then there wouldn't be any heads. Okay, no
Okay,
tails.
thank you.
No heads is the same thing as 2 tails. Okay. All right, then. The simplified addition rule, I'll just write it in here, then I'll show you what it is. This can be used when 2 events, when 2 events are mutually exclusive, which means that they can't both be true at the same time. Okay, so first let me remind you what the rule looks like. The full addition rule, the original one that can always be used, now, when 2 events are mutually exclusive, the consequence of being mutually exclusive is that this intersection has a probability of 0. So what happens is, if that's the case, we don't need to subtract that intersection from here. We can just simplify our rule as the sum of the probability of A and B. We don't need to worry about the intersection because we know that the probability is 0. And this is what we mean by the simplified addition rule. But it only works if A and B are mutually exclusive, because then that intersection has a probability of 0. Now, how about the multiplication rule? That's different. That only works when two events are independent. Okay, so what does that mean? Let's recall that independence indicates two things are true. It means that these two conditional probabilities, for example, this one, what it really means here is that knowing that B is true does not affect the probability of A. And further, knowing that A is true does not affect the probability of B. That's what we mean by independence. Now, the multiplication rule, as it stands, looks like this. And there are two different equivalent ways of expressing it. So what we're going to do here with the simplified multiplication rule is basically assume that A and B are independent. So what that means then is that this A given B can be replaced with the probability of A. And this B given A can be replaced with the probability of B. So let's see how that would look. So you're basically just saying, all right, given that we have independence, both of those conditional probabilities can be simplified as follows. So you end up with something a little bit easier to deal with. But this only works if A and B are independent of each other. So now you didn't have to answer all that. I mean, you just had to say independent, but I just wanted you to see why. Now, complements. For two events A and B to be complements, two things have to be true. Number one, the probability of their intersection is 0. Number two, the probability of their union is 1. Now, I just want to point out that you can also write it like this because it means the same thing. The intersection between A and B is empty, which means they're mutually exclusive, and their union is the entire sample space. So you can pick either or. Either the ones on the left or the ones on the right will prove that A and B are independent. And remember, the example we used was like the red and the black cards in a deck. Okay, because the cards all have to be either red or black, but there are no cards that are both. All right, now the sequences, remember there's only the two types that we wanted to look at. A sequence is essentially a series, it's a group of numbers that have a pattern of some kind to them. Okay, so the arithmetic sequence is the one where a sequence with a common difference between the terms. Such as, so here's an example. And again, you weren't asked to do this, but I want you to see. You can tell this is arithmetic because in order to get from one term to the next, I'm adding 3 each time. Okay. With a geometric sequence, this is a sequence with a common ratio between them. And then that would be something like this: 2, 4, 8, 16, 32, etc. Because we have a common ratio of 2. So down here, we could make the case, and it could start anywhere, by the way. Okay, so now we're ready for problems. Now, here's an interesting one. Based on what we were just doing, you can see we're going to flip a coin 3 times. Now, if that's the case, the outcomes all have some relationship to the flips. So what we're going to do here is try to figure out how many things can happen when you flip the coin 3 times. Now, there's a graph you can use that helps us figure this out. So I'm going to show it to you right now. It's called a binary tree, and it's meant to show what happens after each flip. So we flip the coin and we get either a head or a tail. And once we flip the coin once, the second flip can result in either a head followed by another head, a head followed by a tail followed by a head, and a tail followed by a tail. Then we go the third time. Now, from each of these, there's 2 more possibilities. We can follow this up with another head or a tail. This one can be followed by a head or a tail, a head or a tail, so this row represents our sample space, and it contains 8 elements. And so the way to think about it is that every time I flip the coin, I'm doubling the size of the sample space. So if there was a 4th flip, I would have 16 elements in my sample space. And then a 5th flip, I would have 32. So just remember, the size of the sample space, in this case, doubles each time the coin is flipped. So there are 2 times 2 times 2 outcomes or elements. Sorry, I forgot to write down, equals 8 possible outcomes in the sample space of this experiment. So we've got to get that straight before we do anything else. If you got the wrong sample space, there's no way you can get any of the questions right. Now, once we got that established, normally there's going to be 2 events that we have to worry about. A means, let me copy this down here, at least 1 head. So if you look at all of these flips, at least 1 head means everything except 3 tails. Okay, so I'm going to copy this to indicate that A basically means, oh, what happened?
I have a question.
Yes, go ahead.
How do you know if you go lower or like in the 3rd space? You know what I'm saying?
What do you mean?
Like you have heads and tails, and then you have another heads and tails 2nd space. After the 2nd space, you go to the 3rd space. How do you know when you go further down in the?
You mean if I
Possibility.
flipped it again?
Yeah, how do you know how many possibilities you have to get, like, you know, in order to go to that final sample space that you need to get?
Well, it's just, there's always going to be twice as many every time you flip the coin again. Because no matter what you've done up to that point, the next flip, you'll either get a head or a tail. So you add that to your existing outcome. So like here, when I had H and T, the next flip is either going to be a head or a tail. So HT would be followed by either HTH or HTT. So in other words, for each outcome, the next row, you've got to show that either that can be followed by a head or a tail.
So there's no, like, I mean, is there like a limit to when to stop knowing what you're
Oh,
gonna
well,
have?
for how many, no, I mean, they'll tell you in the question, how many times you're flipping the coin. So if you have three flips, then you stop after three.
Oh, yeah, that's what I want to know because I'm like, how do you know when to stop? Like, those
Oh, because it
possibilities.
says in the problem that there's three flips.
Oh, I didn't see that. I didn't see that. I'm
Yeah,
sorry.
yeah, no, that's why we went three times. If it was only two, you would have had this row up here would have been your second row would be your sample space, but it's because it asked for three. That's how we know that there's 8 outcomes.
Oh, thank you.
Okay, so then A is everything except 3 tails. Okay, so A could be written as, and we could just go borrow them. Let me split the screen so you can see this. Oh, boy, that thing has to get in the way. All right, so I'm just going to copy every one of them except the 3 tails. So you can see there's 7 elements in this set A. Okay, 7, because I'm including everything except 3 tails. And then B is at least 2 tails. So let's see what that's all about. At least 2 tails means HTT. So reading from left to right, we'll write down the ones that have 2 or 3 tails. THT, TTH, and TTT. So that's B. Now, once you've established that, you can answer any of these questions. So for example, the probability of A, because we have 8 equally likely outcomes in the sample space, it's a very simple matter of just counting up how many elements are in A. Let me fix this. Over B, S rather, sorry, number of elements in the entire sample space. Which is 7 out of 8. And then similarly for B, number of elements in B. Over the number of elements in S. 4 out of 8. Okay, now when that's finished, most of these can be calculated very easily from the rules that we know, but C, actually here, there's one extra step with C. The probability of A union B can be calculated from the addition rule.
Sorry to interrupt. Will you be posting your work on these slides?
Am I what?
Will you be posting like the work that we're doing
Yes,
right
yes, yes. All of this stuff I'm doing right now, I'll be posting it on Moodle.
Okay, thank you.
Okay. All right. Now, the one thing we have to do here addresses this part. We don't have that yet. We have to figure that out ourselves. So here's what we need to do. We have to look at the 2 sets and see what they have in common, if any. So let's look at them carefully. Now, if you notice, they both have an HTT, THT, and they both have a TTH, and that's it. That's all they have in common with each other. So the probability of this set is the number of elements in the intersection A and B, A intersect B, over the number of elements in the entire sample space. So that would be 3 out of 8. So if you look at the rule, we already know now all 3 of these probabilities. Okay, so let's bring them together. The probability of A union B, therefore, equals 7/8 plus 4/8 minus 3/8, which is 8/8 or 1. Okay. So basically, you're just combining the information you already have. And then if you look up here, the next question is, what happened here? I lost my place. Oh, it's way up here. Okay. D actually is the probability of A intersect B, which we just got through proving is 3/8 because the intersection has only 3 elements. And there's 8 in the total sample space. Now, E is the probability of, oh, it's the next of the 2 complement rules. Actually, let me split this up again. The complement rules are the easiest ones. Watch how easy this is. The probability of A complement is very simply 1 minus the probability of A, which you recall is 7/8. So you just simply end up with 1/8. And then for F, the probability of B complement equals 1 minus the probability of B, 1 minus 4/8, which is just 4/8. So those are easy. Now, these next 2 are conditional probabilities. We have to remember what those mean. Okay, so here's how they work. The probability of A, now in English, we call this A given B. And it means that we are told that B is true, and now we want to know the probability that A is true. So the formula here is this. In the numerator, you have the probability of both of them. In the denominator, you take the one that's after the slash. In other words, the information that you're given. Now, remember before we showed that A and B had a probability of 3/8 and B was 4/8. So these cancel and you end up with 3/4. So basically, you're just using information you already have. Now, if you notice, H is also a conditional probability, but this time it's B given A. And so the numerator hasn't changed, but remember, A had a probability of 7/8. So when you cancel these out, you end up with 3/7. Okay, so it's all, these 2, it's all about remembering the definition. But for both of them, in the numerator, you have the intersection between the 2. In the denominator, you have this probability. And if you remember that, you're all set. Okay. Now, as it turns out, we have 3 conceptual questions now. They're going to ask us about whether or not the events are mutually exclusive, independent, or complements. Now, we already introduced these earlier. We remember that mutually exclusive means that they have no elements in common or that their probability of their intersection is 0. So when it says are A and B mutually exclusive, answer is no. The reason why is that the probability of A and B is not 0. Okay, which implies that they have something in common. Mutually exclusive means they can't both be true, and they must not have anything in common. But we saw that A and B have 3 elements in common, so therefore they cannot be mutually exclusive. All right, now for J, we want to know if A and B are independent. Well, it turns out that they're not. And why is that? That's because independence requires 2 things. All right, we saw this earlier. Oops. Now, let's check the first one out. The probability of A given B, we figured out a few minutes ago to be 3/4. But A by itself, remember, was 7/8. So we did that earlier. And so what this means is that these two are not equal, which implies, and by the way, we don't have to check the second condition once we know that the first one is false. We have to have both for independence. So this means that the inequality of these two means that A and B are not independent. Okay, now the third and final in this group is are A and B complements? Well, the answer is no. And here's why. Complements require two things, just like with independence. Now, we've already done these, and earlier we showed that the probability of this intersection is 3/8, which is not 0. That tells us that A and B cannot possibly be complements. All right, let me get this back here. Yeah, so that indicates that A and B are not complements. Because already the first condition is false. Okay, now the next question too, is very similar to this one, except for the way the information is expressed. Instead of conducting an experiment, we have, in this case, a bunch of coffee. Okay, so we go to a Starbucks, and let's say this store only has French roast, Guatemala, and espresso. And of course, they're all either decaf or regular. So if I randomly pick, let's say, a bag off the shelf, the chances of it being, let's say, decaf French roast are right here in the intersection of F for French roast and D for decaf. So 18% of the coffees in the store are French roast decaf. And similarly, 10% are regular espresso, 12% are regular Guatemala. And also you can come down here to these totals and you'll discover that 46% are French roast, 22% are Guatemala, 32% are espresso. And it turns out that 50% are decaf, 50% are regular. Now, with that information in front of you, calculating these same probabilities is actually going to be even easier. The ones that require two events to be true, for example, F and D, are especially easy because you can just look these up in the table. So F and D means French roast decaf. Oh yeah, 0.18. R and E is regular espresso, 0.10. F is just plain French roast, 0.46. R is regular, 0.50. So already half of them we've just read off the table. This one is different because it's a rule. It's a simple rule. D is right here. Now, this is the addition rule, but guess what? We can use this simplified addition rule because the columns can't overlap with each other. In other words, there's no coffee that can be French roast and Guatemala. So for these union questions, we can use the simplified addition rule. And so F, as you can see, is 0.46, and G rather is 0.22, 0.68. And similarly, this is the probability of being either Guatemala or espresso. Add up the totals. G has a total of 0.22, E is 0.32. Okay. And then these last two are just what we saw earlier. These are conditional probabilities. And the definition of a conditional probability, again, is that you have the joint probability of both of them divided by the probability of just this expression. So D and F is French roast decaf, which we've already seen is 18%. And F is just French roast, which we've already seen is 0.46. So this ratio is equal to approximately, let me just round that up. That ratio is about 0.3913, let's say. And then finally, this one means the probability of both R and E, regular espresso, is divided by the probability of espresso. So regular espresso is right here, which we saw earlier is 0.10. And it's, all the espressos have a total probability of 0.32 right there. So here we have 0.3125. Okay. All right, so that, it looks like that was it for chapter 11 on this test at least, or at least this problem set. Now we can go back to calculus. Okay, so this is our quick introduction, or overview rather, I should say, of probability theory. So this pretty much covers everything, but there might still be a few other things you might have to do if you go back and look at the chapter 11 problem set, but that covered most of it. Now here we are, we have these rules. Here you're being asked for the first and second derivatives. So because this one is a constant, both f prime of x and f double prime of x are equal to 0. Okay, well, that was easy. Because 0 is a constant, its derivative is simply 0. Okay. Now, what about the next one? Now, this one we have and once again, our favorite rule will be used many times here. The power function rule. Okay. So the first term, we'll have 2 times 3 times x to the 2 minus 1. Now remember, based on this rule, and whenever you have some constant times x, the derivative is just the constant, okay, or the coefficient. The 3 has a derivative of 0. So that leaves us with 6x plus 9. Now the second derivative would therefore simply be 6, because the derivative of 6x is 6, and then here we have 0, so we're just left with 6. All right then. Now C is the product rule. So in this case, the first term is g of x the second term is h of x. G prime of x is just 3 plus 0, which is just 3. H prime of x is just 1. Well, 1 plus 0, which is just 1. So you can plug these in. So remember, we need g of x, h prime of x, h of x, and g prime of x, which is 3. And you can just leave it like that. Although, yeah, in a case like this, since they're asking us for the second derivative, why don't we clean it up a little? It might make things a lot simpler. I like that idea. So now the second derivative will be very simple. It's just 6. Okay. And then finally, we have a quotient rule. Oh, sorry, that's not right. It's h of x squared. So first things first, g of x is the numerator, 2x plus 1. H of x is the denominator, x squared. G prime of x is just 2. h prime of x is just 2x. So let's plug those in. Oh, oops. Wow, what was that? All right, so again, I think what we're going to want to do is simplify this. Now here you could actually simplify it a little by, you notice how both terms have an x in them. We can simplify this as negative 2x minus 2 over x cubed. All right, so let's do that. So that's the first derivative. Now the second derivative, again, it's based on the idea that this is a ratio. This is the quotient rule. So we'll treat this as f of x. So minus 2 minus x minus 2 over x cubed. So g of x and h of x. G prime of x is minus 2. H prime of x is 3x squared. So when we plug these in, we'll have all right, so now we're just going to plug everything in. So let's remind, yeah, there they are. Okay. Okay, so just leave it like that. That's fine. It's such a mess. I mean, you could clean it up a little, I suppose, but it's not really worth the trouble. All right, then we have some basic limits, which is nice. These are straightforward. This is very much like what we had before. The limit of a constant is a constant. Here we're just replacing the x's with minus 4. Very good. Now this next one, it's 1. Three halves. And now this last one, the limit is, we're going to 0. All right. Now here's something we didn't do earlier. This was on the chapter 11 problem set, sequences. So how do these work again? Well, in the first case, we have an arithmetic sequence where, and how can you tell? Because we have a constant difference. So we know that the first term is 0 and the common difference is 5 because I keep adding 5 as I go to the next term. Okay. So with that being the case, I want to know what the 20th term is. So I had this wonderful function to let us do exactly that. So in this case, n is 20 because I'm looking for the 20th term. So I've got a20 is equal to 0 plus 20 minus 1 times 5 95. So I kept writing them out. When I got to the 20th term, it would be 95. And then the sum of the first 20 terms, that formula looks like this. Oops. So S20 is 20 times 0 plus the 95 that we just discovered all over 2. And that turns out to be 950. So in other words, if you wrote them all out, you'd see that the 20th term is indeed 995. And if you added them up, you would get 950. What about this next one? Now, this one is different because this is a geometric sequence. How do you know? Because we're not adding a constant to each term, we're multiplying. In fact, specifically, to go from -2 to 4 to -8, et cetera, the first term is -2, but the common ratio is also -2. So the 10th term comes about as an was a1r to the n minus 1 power. So we're going to have -2 times -2 to the 9th power, because n is 10, and that's going to give me 1024. And then the sum is written as a1, 1 minus r to the nth power, all over 1 minus r. So S20 is -2, 1 minus 2 to the, oh, wait a minute, sorry, it's not 20, it's 10. -2 times 1 minus -2 to the 10th all over 1 minus the common ratio, which is -2. Okay, so now this one's a little messy. -2 to the 10th is 1024. 1 minus a minus 2 is -3. So 2046 over 3 is equal to 682. Very nice. All right, so we just have this last group of combinatoric questions. So remember, in that section, we looked at arrangements, we looked at combinations and permutations. Now we have to remember how to tell them apart and which formula to use. So a restaurant offers a choice of 3 appetizers. Oh, actually, no, sorry, this is not N, this is R, because we're picking R out of a menu of 6 items on the menu. In other words, there's 6 to choose from, and we have to pick 3. The order in which we pick our appetizers doesn't really make any difference. So the number of choices that we have is equal to the number of combinations that we can create when we choose 3 out of 6. So this is NCR. The order doesn't matter. So now we just plug them in. Got 6 factorial over 6 minus 3 factorial, and again 3 factorial. Now here, this is a very simple case. You can actually just write these out. And it turns out that the answer here is just 20. Now, the other option would be for you to write them all out, but that would take way too long. There's no point in wasting your time like that. Now, for B, we have license plates. The state's license plate consists of 5 letters. If no letters may be repeated, how many plates can we create? Okay, now this is different because the ordering of the letters does matter. So if you have a license plate like, let's just mention this, these are permutations. Because just imagine that you pick for your 5 letters, A, B, C, D, E. And you put them in this order, and somebody else has these on their license plate, even though they have the same letters. They're 2 different license plates, aren't they? Because the order matters, not just the letters, but the order. So with permutations, the formula is a little different. Let me just quickly remind you what that is while I'm cleaning this thing up. So we write that as NPR. Now, by the way, we're picking 5 letters from the entire alphabet, which is 26, of course. So therefore, NPR, as you might remember, is n factorial over n minus r factorial. 26 factorial over 26 minus 5 factorial. Now, these are both gigantic numbers. So you may not need to write out those numbers and then divide them. Your calculator may have this already built into it. The TI-84 has the NPR function. If not, if your calculator doesn't have this, you could just type 26x factorial divided by 21 factorial, or 21 times x factorial, equals, and you'd have your answer, which is, it's enormous. Okay, it's 7,893,600. Wow, that's a lot of plates, and that's only with the 5 letters. Okay. So a large state like New York or California, they typically have all the digits can be either letters or numbers, and then there's usually 6 or 8 of them because they need them all. So that's how that one works. And then finally, C, an art gallery has room for 6 cubist paintings to be hung in front of the window. And how many ways can the paintings be hung? Well, those are not combinations or permutations because you're taking all 6 paintings and then hanging them in different orders. So since there's 6 paintings in this case, we would say that each way of hanging the paintings is an arrangement. The number of possible arrangements of n objects is n factorial. So for 6 paintings, the number of possible arrangements is 6 factorial, which is 6 times 5 times 4 times 3 times 2 times 1, which is 720. And that's your final answer. All right, so that appears to be the whole thing. Well, that was long. We covered a little bit of everything. So if you get the sample final, nothing on the actual final will be any different than what we're seeing here. So yeah, that was pretty comprehensive, I must say. So as soon as we're done here, I'm going to post this onto Moodle, and then you'll be able to study from them. Now, if you have any questions, you can send me emails, or if it may be possible to arrange a Zoom conference call. But remember, next Wednesday is our final. So actually, I may be able to get there early on Wednesday to go over it with you as well, if anyone wants that. Normally, I'm not free on Wednesday mornings, but my last Wednesday morning class just ended. So next Wednesday, I could potentially get there early if anyone wants to go over this stuff again. But in the meantime, you can go ahead and send me emails and/or request a Zoom conference, and we'll see what we can do. I should have some more time, more than usual. Not so much tomorrow, but let's say Friday and Monday. Not Tuesday, but this coming weekend, let's put it this way: Friday, Saturday, Sunday, and Monday, it can be done. All right. Tuesday, no, but Wednesday I can get there early if necessary, so we can go over some more questions. All right. So does anyone want to ask any questions right now?
Yes, I do actually. I have a calculator and I looked at the practice samples that you've given us
Yeah.
from chapters 11. And I realized that there's a big difference between the iPhone and the TI calculator when you get the answers. Like I don't know, there's a big difference of the numbers have I gotten.
So what would be
Uh,
an example of that?
So I have practice okay, so if we go to to chapter 11 sample practice number 2.
Okay, let me go get it. Yeah, here it is. Okay, which one?
Question number 4, letter D.
Oh, there isn't a 4.
No, the practice, not the midterm, like the practice, chapter 11.
Yeah, you said number 2.
No, number 4.
No, there's 2 chapter 11 problem sets.
Yeah, if you go number 4, letter D.
All right,
There was a
hold on
big
1 second. Are you sure you're talking about the chapter 11 problem sets?
Yeah, this is it. Yeah, the fractions.
Oh.
Yeah.
Okay, all right, what do you need to know?
No, like there's a huge difference. So I want to know like where's the mode for the TI calculator, because I got a different answer than the iPhone. So I don't know if you require us to use iPhone in the test or you require.
What were you trying to do?
So I was doing this what's it called, the geometric, right? The geometric
Right, yeah,
right, yeah. So I was using that sequence to find the 12th term of like the,
right,
yeah. So and then when I got to the point where I had like 2/5, 3, 1, 4, 4, 1. I tried to
okay,
find that, and
right.
it gave me an answer on the calculator that's so different than the iPhone. Like it's just 0.0001.
Is one of them using scientific notation, maybe?
Um, I did that, but still the same thing. I don't know how the mode of the calculator works. How do you know that?
I think you're gonna have to show me in person. I'm not really sure what's going on. But just look and see if it's scientific notation, because when there's tiny numbers like that, what might be happening is in the Texas Instruments might have a bunch of digits, and then at the end it says E-5 or something like that. That's scientific notation. That might be why it looks different. The
Yeah, that's what
iPhone
I'm
has,
getting.
yeah,
that's
the
what-
iPhone has more room to show you all the digits, and that's why it usually doesn't use scientific notation as often. The TI series, they have less digits on the display, and it's turns into scientific notation much more quickly. So look at the very end of the numbers with your TI 84. And if it says something like E minus 5, that's the scientific notation. It means whatever it says there times 10 to the minus 5th power. So I would check that first to see if maybe that's the reason why you're getting different numbers.
Yeah, that's what I got. E minus.
Yeah,
5.
that's why. So like if it says E minus 6, add 5 leading zeros to what you have there and see if it doesn't match up with your iPhone.
So what I do?
Okay, so what is the actual number you got on the Texas Instruments?
Okay, let me check.
All right.
Hello.
Yeah, go ahead.
Okay, so I did 2 divided by 531,441, and I got 3.763352,846 E negative 6.
Okay, so that means that the actual number, take what you have in the window and put 5 leading zeros in front of that. In other words, it's actually saying that you got 0.00000 and then the 376, et cetera, et cetera. So it's the same number, but they're writing it out differently.
Will it matter in the test if I put it like this way, or should I
No,
put it in
no,
like
either
the
one is
actual-
fine, because I know what it means, like E minus 5 or E minus 6. If you leave that in there, but make sure that's in there. Don't leave that out.
Okay.
Yeah, if you leave in the E part, I'll know what you've done.
Okay. Okay. Yeah, because
Yeah,
I was
it
like,
should be
okay.
fine.
All right. Thank you so much.
Okay, all right, sure. Anyone else?
Oh,
Oh, wait, go ahead.
yeah. Is there a time you're available in your office or anything like that?
Well, it's gonna have to be a Zoom session.
Okay. Okay. Gotcha.
Just send me an email. We'll figure it out.
Thank you.
Okay. All right, anyone else? All right, well then I guess I'll just see you next Wednesday and then we'll just do it and get this over with. All right? So I'll see you all then. And I will, by the way, this recording will also be made available on my YouTube account. Okay, there's no room for it on Moodle, unfortunately, but you'll have that and you'll also have a copy of the solutions. Okay, so I'll just see you next time.
Thank you.
Okay,
Thank you.
all right, bye.
Have a good day. Bye.
You too, bye.